So here we've got an identity that, if you don't know values of some well-known series, looks really surprising. And so what we want to do today is prove this identity without looking at those values of underlying series. So what have we got? We're going to show that 8 times 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1/11, so on and so forth, squared equals 3 times 1 plus half squared plus third squared plus quarter squared, so on and so forth. And so, of course, this left-hand side has something to do with the series involving the inverse tangent, which will give us some value of pi. And then this right-hand side is the famous Basel problem. But if we don't know those, this looks surprising because we've got this square out here on this infinite series, and it looks like this square is coming inside and squaring everything, and then also including the even terms. And so I really like series that look surprising like this, even though I think the fact that they look surprising is kind of just an artifact of our number system. So anyway, let's get going. So the first thing that we're going to do is define a certain function. And I should point out that I found this on the Math Stack Exchange. Okay, so let's define this function that we'll call f. And so f of t will be equal to, so it's piecewise defined. So it's going to be 1/2 times pi minus t. And so that's when t is between 0 and pi, not including 0. It's going to be 0 when t is equal to 0. And then it's going to be, let's see, minus 1/2 pi plus t if t is between minus pi and 0. Again, not including 0. And then, well, that's not everything about the function. Also, what we want to do is extend so it's 2 pi periodic. Okay, nice. But anytime we've got a function that's periodic, we can find its Fourier series. And so that's what we want to do now. So I'll just remind ourselves that we should be able to express f of t as a naught plus the sum as n goes from 1 up to infinity of a n times cosine of nt plus b n times sine of nt, where these coefficients a0, an, and bn are formed out of some well-known formulas. And in fact, let's make those calculations right now. So let's note that a naught will be equal to 1 over 2 times pi, and then the integral from minus pi to pi of f of t dt. Now, I'd like to point out that these come from a derivation, which I think we've done on the channel before, but we're not going to repeat it here. And so I'd like to observe that our function f of t is odd. And so that means this integral from minus pi to pi is simply going to give us 0 very, very quickly. Okay, and then our an terms will be given as, let's see, it's going to be 1 over pi, and then the integral from minus pi to pi of f of t times the cosine of nt dt, which again is going to give us 0. In this case, we've got our odd function f multiplying an even function cosine, giving us, in the end, an odd function. And now, finally, we have bn is equal to 1 over pi times the integral from minus pi up to pi of f of t times the sine of nt dt. Now I'd like to observe again that f is odd, sine is also odd, making their product even, which means I should be able to multiply this by 2 and then change these bounds of integration from minus pi to pi to 0 to pi. And I'll do that simultaneously while taking the 2 associated with the change in bounds and canceling out with this 1/2. So that's going to leave us with a 1 over pi and then an integral from 0 to pi of pi minus t times the sine of n times t dt. And now we can perform a round of integration by parts on this. It shouldn't be too bad. So let's do it in the tabular method. So let's see, we've got our polynomial term here, pi minus t, and then our transcendental term here, this sine nt. We'll take derivatives down this column, so that'll give us minus 1 and then 0. We'll take antiderivatives here, so that's going to give us minus 1 over n times the cosine of nt. And then let's see, 1 over n squared minus times the sine of nt. And now we'll match on the diagonal and alternate the sign, and that should be what we need to take this antiderivative. Okay, so let's see if we can write it down now. So we're going to have this 1 over pi out front, and then we're going to have a minus 1 over n times this pi minus t. I'm going to subtract, or I'm going to cancel the minus signs to leave this as a t minus pi over n times the cosine of nt. And then let's see, we've got 1, 2, 3 minus signs built into this, so I'll use those to cancel all down to a single minus sign. So minus sine of n times t over n squared. Now we need to evaluate that from 0 up to pi. So notice evaluating this whole thing at pi will give us 0. Here we get this 0 in the numerator. And then let's see, over there we get a 0 because sine of n times pi is 0. And now let's go ahead and evaluate this at 0 and observe that we're going to get a minus 1 over n from this first term and a 0 from the second term. But 0 is the lower bound of integration, so that's going to flip that back up to a positive 1 over n. Okay, nice. So now let's maybe summarize what we've done over here and then move on. Thanks for sticking around this long into the video. If you're enjoying the video, make sure and give it a thumbs up. And if you're not yet subscribed, consider subscribing. It really helps us out. So previously, we took this piecewise defined function that was extended so that it was 2 pi periodic and found its Fourier series, which gives us really just two ways of expressing this function, either as piecewise extended or as this sum of sine type terms. And now looking at this, the fact that we've got a square here, that motivates that we should probably look at the square of this function, and that's exactly what we're going to do. So maybe we'll say f of t squared on the one hand is going to be this object right here squared. So let's see, we can write that out in its piecewise method as 1/4, and then we'll have t minus pi quantity squared. I'll take the fact that we're squaring it to change the order of subtraction just so it's a little nicer. And that's going to be when, again, t is between 0 and pi. It's going to be 0 when t is equal to 0. And finally, it's going to be 1/4, and then t plus pi quantity squared if t is between negative pi and 0. Okay, nice. But now let's square it in this other way as well. So we've got f of t squared is also equal to the sum, as n goes from 1 to infinity, of sine squared n times t over n squared. Of course, those are just the diagonal terms in the square. We also have the off-diagonal terms, which I'll just summarize as the sum as m is not equal to n. They're both going from 1 to infinity, but I'll just leave that out and say m is not equal to n of sine of mt times sine of nt over m times n. Okay, so now that we've got that written down, let's put that over here to the left, and then we'll do the last couple of steps. Before we jump back into the problem, I'd like to thank my channel members and patrons, which help keep my second channel, which is focused on mathematics learning with full courses from upper division math classes, ad-free. If you'd like to help out with that, but no pressure, think about becoming a patron or a channel member. Okay, so let's recall that we had this function f, which had a piecewise definition and a series definition as this sum of sine nt over n. And then we looked at its square, which I've renamed g, and we wrote that in a piecewise definition and with this series definition. Now we're ready to do our final calculation, and it's going to kind of start at a crazy place. So let's start over here on the left-hand side, but multiply it by pi. So that means we'll have 8 times pi, and then 1 minus a third plus a fifth minus a seventh plus dot 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 squared. But now I'd like to observe that the stuff inside of this parentheses is simply f evaluated at pi over 2. And so why is that? Well, that's because if you've got an even number times pi over 2, then you'll have sine of an integer times pi inside of this, but that's going to give us 0. And then sine of an odd number times pi over 2 will alternate in this method right here. Okay, so that means we can rewrite this whole thing as 8 times pi times f of pi over 2 squared. In other words, g of pi over 2, given the fact that I've defined g of t to be f of t. Okay, great. But now here comes like kind of a crazy place, and that is now we are going to evaluate g using this piecewise definition over here, and then multiply it by 8 pi. And you'll see what we get in that case is pi cubed over 2. And so that's a pretty easy calculation. If you evaluate this at pi over 2, so let's observe that from this part right here, we're going to get pi over 2 squared. That's going to be pi squared over 4 times this other 4, which is going to give us 16. Multiply that by 8. We're going to have a over 2 there. I should point out here that this should have been a pi cubed. We pick up that extra pi from the one that I mysteriously multiplied out on the front. And now next up, I'm going to multiply and divide by 3. So I'm going to write this as 3 times pi cubed over 6. But now that I've gotten that written as 3 times pi cubed over 6, I'm going to go ahead and take that and write it as 3 times t minus pi cubed all over 6, evaluated from t equals 0 up to t equals pi. And so obviously evaluating that at t equals pi will give us 0. Evaluating that at t equals 0 will give us a negative pi cubed over 6, but it's the lower bound of evaluation, so that picks up a minus sign. But now I'm going to think about this evaluation as a 0th integral, and then take the fundamental theorem of calculus to write it as a first integral. Okay, so let's see. If we do that, we're going to have that this is equal to 3 over 2 times the integral from 0 up to pi of t minus pi squared dt. Okay, great. So taking that derivative to change it from a 0th integral to a first integral, cancel the 6 in the denominator down to a 2, which I brought out. Okay, so next up what we're going to do is take this 2 in the denominator, exchange it for a 4 in the denominator at the cost of multiplying by 2. So that's going to give us 3 times 2 times the integral from 0 to pi of 1/4, and then we have t minus pi squared dt. But that's simply the integral of g from 0 to pi. So we can go ahead and write that as 3 times 2, and then the integral from 0 to pi of g of t dt. Now we're going to use the fact that g is even, which we did before, to exchange this 2 for a larger bounds of integration. So that's going to be 3, and then the integral from minus pi to pi of our g of t dt. Now we're going to exchange this version of g that we've been using, the piecewise version of g, for the series version of g. So that's going to leave us with 3, and then we'll have the sum as n goes from 1 to infinity of 1 over n squared, and then the integral from pi minus to pi of sine squared of n times t dt. And then we'll have plus the sum over m not equal to n of 1 over m times n, and then the integral from minus pi to pi of sine mt sine nt dt. And then I think it's well known that the sine function, or sine mt and sine nt, are orthogonal, where we view this as like some sort of inner product. And so This integral right here will give us 0. And then next up, we can perhaps use a power reducing formula on this first integral. We can take that and we can rewrite it as 1/2, and then we'll have 1 minus the cosine of 2 times n times t. Okay, great. But what I'd like to do is take this 1/2, get rid of it by taking this minus pi and exchanging it with 0. Again, using the fact that sine squared in this case is even. Okay, and then let's see, what are we going to be left with? We've got 3, and then the sum as n goes from 1 up to infinity of 1 over n squared. And then we've got the integral from 0 up to pi of 1 minus cosine of 2nt, and then dt. And now, pretty easily, it's seen that if we integrate cosine, we'll get a sine. Evaluated at pi and 0 will give us 0. So this cosine term isn't really contributing anything. The only thing that's contributing is the 1 term. But integrating that out and evaluating it from pi to 0 will simply give us pi. So in the end, we're going to have 3 times pi times the sum as n goes from 1 to infinity of 1 over n squared. In other words, we're going to have 3 times pi times 1 plus a half squared plus a third squared plus a quarter squared, so on and so forth. But now if we look over here at the extreme left and the extreme right of our equation, if we cancel the pi's, we get the formula that we were going for. And that's a good place to stop.